Thank you. So we're a minute or so ahead of schedule here, so we can get started in just a moment with our final adaptive optics talk today, where Gemini's Paul Hirst will discuss the ground layer adaptive optics feasibility study that we recently conducted for Gemini North. And I think, Paul, you could go ahead and start now. We're only just a few seconds ahead of schedule at this point. Perfect. Thanks.
Cool. Thanks a lot, Henry. Yeah, so as Henry just mentioned, I'm going to tell you about this ground layer AO feasibility study. I'm presenting on behalf of a fairly large team of people at Gemini who have been involved in this. I've got the list of names up on the screen there. So thanks to all my teammates on this. So ground layer AO, I think people are probably familiar, but just as a quick reminder, the baseline here is that we only attempt to correct the ground layer turbulence, so the turbulence in the atmosphere just above the telescope. We ignore all the turbulence at high altitude. And that gives us a lower fidelity correction. The baseline we're looking at for a system like this is a factor of 2 smaller point spread function than natural seeing, but a large field of view. So the design we're looking at here would support the entire GMOS imaging field of view, for example. The idea we're looking at is to use an adaptive secondary mirror, as has been mentioned, and to use the laser guide star facility from the GNAO project that Gaetano just mentioned, which gives us 4 10-watt sodium sideward LGS beams. For the NGS side, the tip tilt and slow focus, the concept we're looking at is to use P2WFS or the OI on instrument wavefront sensors. We may need to do some upgrades to those to get the kind of performance we need. I'll come back to that in the talk. So adaptive secondary mirrors, what's the deal here then? So the idea is that the secondary mirror of the telescope becomes the deformable mirror for your adaptive optics system. There's essentially 2 vendors of these right now, Adoptica, who you can see one of their mirrors on the left here, and TNO, you can see one of their mirror designs on the right. The principle to the first order is very similar. There's a thin face sheet, they call it, which is a piece of glass, a couple of millimeters thick, so it's very thin, silvered on one side. We will coat it in our regular coating chamber that becomes the front surface, a reflecting element of the mirror. And then you have a number of actuators where we'd be looking at, we don't have an exact number, but of order of magnitude 1,000 actuators or slightly less. But you have all these actuators that push and pull on the back surface of that piece of glass in order to bend the glass, and that makes it your deformable mirror. And the Adoptica design uses a magnetic voice coil arrangement. So you have all these little magnets glued to the back of the glass face sheet. And then the actuators have voice coils, which are little, copper solenoids, which push and pull on those magnets to bend the glass. The TNO design is actually quite different. The actuators are these little yellow cylinders down here. These work on a magnetic reluctance principle, and they have a physical push rod up to the back of the mirror. The 2 different technologies both have very different pros and cons. They both have their strengths, they both have their challenges, but there are two potential vendors out there. So why would we want to do GLAO with an ASM? So as I mentioned earlier, the baseline is a factor of 2 improvement in image quality. So your regular kind of common or garden 0.6 arc seconds natural seeing becomes 0.3 arc seconds with GLAO, which I think you'll all agree is pretty good. This benefits both angular resolution, obviously if you're trying to resolve structure in sources, but also if you're just looking at point sources, especially in the infrared, you get a huge sensitivity improvement simply because you can use a smaller aperture because the point spread function is smaller. So you get less skylight in the aperture and therefore less noise. The arrangement we're looking at has no throughput or emissivity penalty. So the throughput of the AO system, if you like, is 100% and the emissivity is 0%. Because there's no AO bench in the system, there is no additional optics in the science path. We simply replace the regular mirror with an adaptive secondary. And we don't take up an instrument port, and we can feed light to any of the instrument ports. So it really does become part of the telescope. And you could imagine a future where using GLAO becomes the default, just like we use tip tilt guiding currently. Nobody thinks about observing without tip tilt guiding or active optics on Gemini. And we could envisage where GLAO becomes similar, and who doesn't want better seeing? Now, there is a big caveat here. We do need the laser guide stars, and we can only propagate the lasers when the skies are clear. So that is the main limitation. We just did a user survey targeted to people with who've had similar kind of science cases or proposals before, and we've been reviewing some science cases from existing work. And many thanks to those of you who responded to the user survey. It shows very strong support for the concept with a wide range of science cases, which is really good to see, really gratifying. So why are we doing this feasibility study now? So we actually considered GLAO in the original concept for what became GEMA and GNAO. And it became apparent during that there's some pretty big unknowns. We didn't really have a design of how we could implement this on the telescope. We had some kind of ideas, but no more than that. And the cost was really unconstrained. We really didn't have a good grip on how much it would cost. And of course, it's difficult to write a proposal on that basis. So it was descoped out of GEMA GNAO because of that. And the solution, the way forward, of course, is to carry out this feasibility study to figure out if we do have a viable way to put this on the telescope and to get some idea of the cost. And if we can do that, then we're well placed to respond to subsequent funding opportunities. So the challenges, why is this so difficult then? So in my view, there's two real challenges here. The first is kind of obvious. Can we procure a suitable adaptive secondary mirror and mount it in place to the current M2? Now, we have to remember it needs to be able to maintain all the functionality of the current secondary mirror system. So tip, tilt, focus, all that kind of stuff, we need it to do as well. There are quite a few operational challenges associated with ASMs. I don't have to go into details, but there are some ASMs out on other telescopes, and you know, the technology is improving, but there are challenges there. The real difficult question, on the ASMs, as I mentioned, there are vendors that can design and build ASMs for us, so it's doable. The real difficult question is, where do we put the wavefront sensors, specifically the laser guide star wavefront sensors? So the acquisition and guiding unit on Gemini is really very space constrained. Let me just skip on to this next slide. This is the cartoon off the website of the ANG. So as a reminder, the ANG sits in the center of the instrument cluster on the back of the telescope. And it has the peripheral wavefront sensors, acquisition cameras, and the science fold, which directs the light out to whichever instrument port you're using. Now, earlier concepts for GLAO on Gemini envisaged the kind of somewhat obvious arrangement where you replace the science fold mirror. Right now, it's a fully reflective mirror. If you replace that with a dichroic mirror, so you transmit the visible light straight down to a set of upward-looking visible light wavefront sensors, and you send the infrared light out to the 4 science ports. That's all good, but sounds good, but there's a problem with that. And the science fold is actually quite big. And right now, it being a fully reflective mirror, it has a metal structure behind it which supports it and holds it flat. As the telescope tips around the sky, the science fold goes through almost every possible orientation, depending on which instrument you're using and this kind of thing. And it turns out if you want to, well, obviously, if you want to have a dichroic science fold, you can only support it around the edges. You can't have a metal lattice behind it because some of the light is going straight through. And if you have such a large piece of glass only supporting it around the edges, as you tip the telescope around the sky, it sags under its own weight due to gravity, too much to keep it flat within AO tolerances. So you lose optical quality because of that. So that doesn't work. So we're looking at other ways to do this. If we can't separate the LGS and the science light with a dichroic, maybe we can separate them spatially. So you look at the ANG stack here. So module 3, for example, this is where P2 WFS sits. I should have just mentioned, it's maybe not obvious. When the system's assembled, these units kind of fit inside each other. It's a kind of concentric rings that's, you know, the science fold slides up inside module 3, for example. So you look at this and you think, well, there's some empty space on module 3 here. Maybe that would work. Well, over on the right here, this is a photo of the actual module 3, and you can see there really is no extra space on there. So it really is very space constrained in there. So let's have a look at the way light passes through the telescope then, thinking about a science beam and a guide star beam. So the diagram on the left is a kind of schematic view of the center of the telescope. The blue line in the middle represents the primary mirror. This kind of truncated cone at the top, this is the M1 baffle, the black tube which sticks up from the center of the primary mirror. You see in photos of the telescope. And then underneath, we've got the ISS and the ANG. And the beams I've shown here, the green lines denote a science beam at the edge of the GMOS science field of view, the GMOS imaging field of view. And the yellow lines denote light from a laser guide star. So these both come from the secondary mirror up at off the top of the screen and come down to focus at the back of the telescope here. So you'll notice that the laser guide star light comes to focus significantly behind the science focal plane. And that's because the lasers illuminate the ionosphere. There's a layer in the ionosphere with sodium ions about 90 kilometers. So the LGS light doesn't actually come from infinity optically like the science light does. And the result of that is that it comes to focus behind the science focal plane. The other effect of that is that as you go up the telescope, the LGS beam is actually wider than the science beam because it's not coming to focus as quickly. So we have these two beams and we're looking at separating them spatially. So obviously they overlap completely at the secondary mirror because the secondary mirror defines the pupil of the telescope. And at the focal plane, they're completely separate. So there's a point in the middle that we've labeled this beam separation point. And that's basically the point where the two beams don't overlap anymore. You can imagine if you make the science field smaller, if you move the green beam to the right, then that point moves higher up in the structure. Likewise, if you make the LGS asterism larger, if you move the yellow beam out to the left, then you get the same effect, that point zips upwards in the structure, which is great because the higher up in the structure that is, the easier it is to separate these two beams. But there's a catch. If you move the LGS beam too much to the left, then it starts to vignette on the M1 baffle, as I'm showing in the middle picture here. We don't want to change this baffle because it's there for a reason, providing optical baffling on the telescope. But we do get this slight vignetting of the LGS beam on that baffle, which I'll come back to discuss later. So looking at this beam separation point, I've got a plot here showing on the y-axis the height of the beam separation point up the telescope, the distance from the focal plane. So basically how high in the structure the beams separate. And on the x-axis, I've got the LGS asterism size. So you can see as we make the different colored lines then represent different science fields of view. So you can see as we make the asterism larger, as we go to the right, then the beam separation point moves up through the structure. And as we make the science field larger, then the beam separation point moves down in the structure, hovering between these lines. And on the y-axis, these dashed lines represent some of the crucial parts of the A&G structure. So P1 WFS, the P1 rotary table, P2 WFS, the P2 rotary table, and the science fold. So we'll come back to that point, that plot in a second, but you can see from this, we want to go to the right on this as a big driver because the bigger asterism gives us higher up in the structure for a given field of view. But if we go too far to the right, if we make that asterism larger, we hit this LGS vignetting issue that I just mentioned. So the question is this a problem? Well, it depends how big you make it. So if we look at this plot on this diagram on the left, so what these diagrams are showing, this is the pupil of the telescope, if you like, as seen at the wavefront sensor. And the different colored lines drawn on here represent the areas which will be illuminated by the 4 different laser guide stars. So we would have 4 laser guide stars, 4 laser wavefront sensors, 1 on each of the guide stars, and they're in a square around the telescope. So the vignetting from on each of these would be kind of at a different quadrant of the pupil, if you like. So the area in the center here, the vast majority of the area is covered by all 4 laser guide star wavefront sensors just fine. It's just that each of the wavefront sensors has one of these little crescents around the edge, which would not have any light coming through to it and would give us no measurements of the wavefront. Now, if you make the LGS asterism even bigger, what happens is these crescents start to overlap. So in the center image, you can see they're just kind of touching, but over on the right, if you go to a really big asterism, you've got these fairly big divots, which are vignetted on 2 of the 4 wavefront sensors. So essentially, we had a bit of a hypothesis that for GLAO, if every point on the pupil is covered by at least 3 of the wavefront sensors, that seems kind of viable. As a reminder, most of the pupil is covered by 4, but there are these crescents where there's only 3. So what we did some fairly simple AO simulations of a GLAO system with this, thanks, I see the stars there, with this vignetting of the LGS light. And we've got some delay, here we go. So this is what we've got. So the purple line is natural seeing, the open loop line is natural seeing, the red line is the closed loop, the GLAO system, and you can see the model reproduces pretty well this factor of 2 in image quality that we sort of stereotypically expect for GLAO. So we're coming from, the 0.5 comes down to the sort of 0.25 region and so on. Now, just to stress, this model was specifically to investigate this vignetting issue. There are probably a lot of effects in the actual system which are not modeled in this model. So the simulation is probably very optimistic where you see it getting close to the diffraction limit. There's undoubtedly other things in there which will degrade the performance. But the point being that we confirmed that if we have these little crescents vignetting on the LGS, as long as they don't overlap, then the AO performance seems good. So we can mark this back on the plot that I showed earlier. So this is the same plot with some extra stuff overlaid. So if we make the LGS asterism too large over on the right, we're going into this red area, and we're losing AO performance because of the LGS vignetting. If we try and go too far down in this plot, if we try to separate the beams at the science fold level, for example, we really don't see any way mechanically to do that. So what I've labeled as increased A and G complexity is really kind of impossible design. But also the other driver, of course, is we want as large as possible science field of view. So that points us to this area with the green dashes around it here, nestled in this little corner, which looks quite optimistic because this is the 6 arc-minute science field of view. So we're about the size of the GMOS field. And it suggests to us that we should be looking at picking off the light round about the P1 level, where the beams will separate, and that looks a viable design. So the question is, can we find a way to do that? Well, actually, yes, we can. So it just so happens that there are some holes in the sides of the A and G, the acquisition and guiding shell, that lead to available space volumes in the mirror cell. Honestly, I'm not sure what the original idea was for these holes, but there are these holes that lead from the A and G into the mirror cell. So the concept we have is to insert these deployable LGS pickoff mirrors into the beam. They'll swing down from above the P1 level to be in the beam around about the P1 WFS level, bounce the light back up and out of these holes in the side of the A and G. You can either go out the other side, or the way it's drawn here, you could actually, there's an alternate design which bounces the light across to the other side. Either way works. And then we can locate the actual wavefront sensor optics and the detector and all that kind of stuff way out here in the mirror cell, out of the way of everything else. Here's some 3D renderings showing what that would look like. I'm not going to go into details on these, but it looks like we have a viable way forward. So there are some open questions, though, specifically with regards to the natural guide star wavefront sensing, which we need for tip tilt and slow focus with an LGS system. So the baseline idea we have in mind is to use P2 or OI for this, just like we do for natural seeing right now. The question is, are they sufficiently fast and sensitive to give good sky coverage? So we haven't done the simulations yet to figure out how fast we need to do NGS tilt. That will tell us how bright the guide stars need to be. There's some other complications. The LGS pickoff mirrors will vignette the P2 and OI patrol fields somewhat. So the area of sky available to the guiders will be smaller. And the LGS asterism, and thus the pickoff mirrors, are fixed relative to the telescope. They don't track on the sky. So stars, NGS stars, will rotate round through that vignetting pattern through the gaps. So we would need some software handling of that. Now, the observatory is investigating upgrades to P2 and OI anyway. We just don't know yet, but it could be that these upgrades become prerequisites for doing GLAO. Basically, if we get higher sensitivity on those wavefront sensors, we can guide equally fast on fainter stars, and that will recover the sky coverage for us. So in summary, we found feasible solutions to the major challenges of implementing GLAO on Gemini. There's some compromises, but we don't think they're an issue. The concept we have supports all instrument ports, doesn't take up an instrument port, and incurs absolutely no throughput or emissivity penalty. It's very well integrated with the telescope. But just to stress, this is a pre-conceptual design stage feasibility study. Many questions do remain unanswered, and continuation to conceptual design stage and beyond is not currently funded. The idea here was to basically be ready to go if a funding opportunity arises. And we think we have a viable concept ready to go that should be good to go to conceptual design phase should the opportunity arise. Okay, thank you.
Thank you, Paul. Let's see, I see a question in the chat, but it's actually marked as having already been addressed there.
Cool.
And I do see another, yep, yeah. This is the good thing about having colleagues online simultaneously there. Let's see.
Awesome, yeah.
Navigate back. I do see a new question. Would it use only one NGS with either P2 or OIWFS, or ideally you'd like to use more? The plot showed 3.
So we haven't really done the modeling to that level, but actually we would expect that one would probably be fine. But well, maybe I'm speaking a bit ahead of myself there. We haven't really modeled this. Hopefully one would be fine. We don't really have anywhere to put extra NGS wavefront sensors without vignetting the science beam. So we're kind of hoping one is good. It's GLAO, so the isoplanatic patch, if you like, or the iso tip tilt patch is pretty large. So it's really only tip tilt we're looking at here. In an MCAO system, if you're a multi-conjugate, then you need multiple NGS stars because your plate scale modes are unconstrained. We're a single conjugate system at the ground layer. So there is no degrees of freedom in plate scale in the DMs. You need 2 M's to do that, 2 DMs to do that. So hopefully one should be adequate. I wouldn't imagine that tip tilt variation across the field would be significant at the level of correction we're looking at. Remember, we're not looking at a high Strel ratio correction. We're looking at a factor of 2 in image quality. So the isoplanatism errors in tip tilt would probably be pretty small compared to those introduced by the high level uncorrected turbulence, for example.
Great, thank you. And with that, it's going to be time to move on to the chat session. So thank you, Paul, and thank you to all of the speakers in today's sessions. We very much appreciate it, and we appreciate everyone who has been attending and listening in here. Janice, do you have any announcements before we move on to the chat sessions and then the TOO workshop after that with Brian Miller?
Nope, I don't have any announcements. Joe, anything on your end?
Just to make sure to come back for Brian's workshop after the chat sessions. I'll be here waiting.
Perfect. Perfect. Thank you, everyone. See you at the TOO workshop and see you in the sessions tomorrow. Thank you.